Right. I think it's time. Welcome, everybody, to PALS. Today, Moritz Schöbi from Technical University Vienna will talk about eliminating and enforcing injectivity in infinite domain constraint satisfaction. Please, Moritz.
Thank you for the nice introduction. Yeah, as Peter already said, I'm going to talk about eliminating algebraicity and enforcing injectivity in the context of infinite domain constraint satisfaction problems. Before diving right in, I want to give you a short overview of what I want to be talking about today. So I will try and begin by setting the scene, give you a short insight into what constraint satisfaction problems actually are. I tried to keep it short because I think there have been many talks about this in the recent past. Then we will dive into infinite domain CSPs and look at the Boudirsky-Pinsker conjecture, around which the entire talk will then somehow orbit. We will then discuss three questions we posed around the scope of this conjecture. I will then provide three short answers to these questions, and then afterwards dig a bit deeper and show you a construction and give you an idea how to prove the answers to two of the three questions. One quick thing I forgot to say, this talk is based on joint work with Michael Pinsker, Jakob Ritval, and Christoph Spies. Okay, so let's get started with constraint satisfaction problems. As I said, I'm going to keep it short. For our purposes today, I will often write this structural A. This will always be a relational structure with a finite signature, usually tau, and it will always be countable. And for such a structure, the constraint satisfaction problem, or the CSP of A, is defined as the computational problem where given another finite, another structure of the same signature, finite, in our case I call it C, we ask whether this structure maps to A homomorphically or not. Many computational problems can be phrased in this way. For example, a very well-known one is the so-called three-coloring problem, where we ask whether a given graph, in our case here always a finite graph, can be colored in a way such that two adjacent vertices never have the same color and we only use three colors. This can be phrased as the CSP of K3, the complete graph with three vertices, so just a triangle. And this problem is famously NP complete, so as hard as an NP problem can be. Yes, before showing you probably the most exciting or well-known result in CSPs of the last 10 years, before showing that, I need two more notions. Namely, we say that a structure A, a relational structure A, PP constructs another structure, B, if B is homomorphically equivalent to something that we can PP define, so using primitive positive formulas, so existential quantifiers and conjunctions of positive atoms, that we can PP define in a finite power of A. In this case, if we can construct B from A in this way, then the CSP of B reduces to the CSP of A, meaning that it is at most as hard as the CSP of A. In particular, if A PP constructs K3, this means that the CSP of A has to be NP hard. And the next notion, the last notion before we can get to the first theorem, is that of a polymorphism. By polymorphism, I just denote all homomorphisms from finite powers of A into A itself. Okay. So yeah, this is the celebrated result I talked about before, proved independently by Bulatov and Zhuk, both in the year 2017. And they proved a conjecture by Feder and Vardi about finite domain CSPs. Namely, for finite relational structures, there are just two cases of how hard their CSP can be. in terms of P and NP. There is a dichotomy, namely either the CSP of A is NP complete or it is polynomial time solvable. There is nothing in between. And even more than that, we can see how hard this problem is going to be by looking at the structure, namely the CSP of A is NP complete if and only if A constructs K3 via these primitive positive definitions in the power. And the CSP is tractable, so polynomial time solvable, if and only if the polymorphisms satisfy a very specific identity. This identity of a six-area polymorphism that's called the Siggers identity. There are multiple identities like this that are equivalent, but this is the one I'm going to use today. And ever since then, the big goal, or even a bit before that, the big goal of infinite domain CSPs has been to maybe lift this dichotomy as far as possible to the infinite case, and maybe also show similar things in this setting. One step in this way is the so-called Bodirski-Pinsker conjecture, which I'm going to talk about now. Now we are dealing with infinite structures, and we only can work with particularly nice ones that are somehow close to finite in a setting, in a way. And two notions needed for that are homogeneity and finite boundedness. First of all, we call a relational structure A homogeneous if every isomorphism between two finite substructures of A if every such isomorphism extends to an automorphism of the entire structure. As an example, we have Q with the order. You can imagine this finite substructures, so just three dots in Q, and another one. If we then have a local isomorphism between those two, so just an increasing mapping from the first three to the second three, we can always extend this by piecewise linear transformations to an increasing bijection of Q itself, and so an automorphism of Q. And the second notion we need is finite boundedness. We call a structure A finitely bounded if there is a finite set of finite structures in the same signature as A, such that for all finite tau structures, so again, same signature, we have that these structures we embed into A if and only if they do not embed any structure from this finite set. So one could say that a structure B embeds into A, or up to isomorphism, is a substructure of A if and only if it avoids a finite set of forbidden patterns in a way. Again, a very nice example of a finitely bounded structure is Q with the order, this relational structure here. Just thinking about how finite substructures of Q can look like, so finite linear orders. Well, the axioms for that would be, we want them to be irreflexive. So we forbid the pattern that some x is smaller than itself, forbid loops. Then we want the order to be total. So we forbid x and y that are not comparable, forbid this substructure. And we also forbid intransitivity. So we forbid pairs, triples x, y, and z, such that x and y are in the order, y and z are in the order, but x and z are not. And once we forbid all these three, we have satisfied all the axioms of a linear order. And so we embed into Q. Actually, it's not a surprise that I use axioms here, because in the context of homogeneous structures, which Q is, being finitely bounded is just the same as having universally quantified axioms for all finite substructures. Okay, having these nice infinite structures, we can formulate the conjecture, the Bodirski-Pinsker conjecture. It has been formulated, as it says here, in 2011, but the formulation that is here is a bit more modern, using some newer results. or newer notions that make it more nice to state. So given a structure A, that's a reduct of a finitely bounded homogeneous structure. So B is finitely bounded and homogeneous, and A is just made from B by forgetting a few relations. In this setting, the conjecture says that also one of two cases holds. Either, same as in the finite case, a PP constructs K3, and so the CSP is hard, or the polymorphisms of A satisfy a certain identity, and the CSP is tractable, so polynomial time solvable. But, however, here we have a different identity. We have the pseudo-Siggers identity. So not only the Siggers with this S of 6 arguments, but we post-compose S with 2 endomorphisms, alpha and beta. And so this identity has become a bit weaker in this case. And this is no surprise in the infinite case. As we will see later, this is actually even necessary. This will be one of the results I'm going to talk about later. Okay, around the scope of this conjecture, so around these reducts of finitely bounded homogeneous structure, we asked a few questions that you can see here. Above, I just copied the conjecture, so you don't need to reread that. But we asked whether we could impose additional structural assumptions on these structures. So could we assume more about this A without losing generality? So yeah, without changing the truth value of the conjecture. The second question was whether we could make any additional significant algebraic assumptions on the polymorphisms of A, again, without losing generality. And the third question went a bit in a different direction. There we asked what links there would be between the CSPs from the conjecture, so CSPs of reducts of finitely bounded homogeneous structures, and so-called promise constraint satisfaction problems. I will introduce what they are when answering the question. Yeah, so let's dive right into the first short answer to the first question. So can we impose additional structural assumptions? And the answer is, I guess, at this point, unsurprisingly, yes, we can. Namely, given A, reduct of a finitely bounded homogeneous B, we find new structures, A star, a reduct of a finitely bounded homogeneous structure, B tilde, I called it here, such that nice properties of A and B also transfer to these new structures. PP constructibility of K3 is also transferred from A to A star and backwards, so yeah, equivalent in this case. The CSPs of the two are efficiently interreducible. I will dive into what that means a bit later. And this is now the strong assumption we have. A star has no algebraicity. This is the new assumption we could impose. So we did not change the complexity of the CSP. We did not change PP constructibility of K3. We did not change being a reduct of a finitely bounded homogeneous structure. Now B tilde instead of B. But we could impose no algebraicity. In the long answer, I'm going to show you what that is good for. Yeah, that's the first short answer already. The second one, revolving around polymorphisms. So can we impose any significant algebraic assumption on the polymorphisms? And actually we can. Namely, because we got rid of algebraicity, we can now do a further construction. We can expand this new A star that we got in the first answer by a relation, a new relation. We can add this relation such that this resulting structure will only have essentially injective polymorphisms. What this means is that all polymorphisms of this new structure we get have to be injective with respect to all variables that they actually depend on. So, of course, if you have a function in many variables, you can always add dummy variables that don't do anything, and the resulting structure will still be a homomorphism. But if we remove all up to dummy variables, if we remove all dummy variables, the things that remain have to be injective. And in particular, this means that when talking about these identities that could characterize tractability in the infinite case, or in the reductive finitely bounded homogeneous case, we have to use somehow injective or essentially injective identities. Others have no hope of working because we can always assume that only such polymorphisms exist. Yeah, that's the second short answer. The third one will be a bit longer because I want to introduce what promise constraint satisfaction problems actually are. And also, I will not go into the construction or the proof of this later. So I will do this at the medium speed. Yeah, what is such a problem? This is a generalization of CSPs. And we will only do it for finite structures today. So given two now finite tau structures, not one, but now two, such that the first S1 maps to S2, the PCSP of the two is the computational problem where, again, given a finite tau structure, we ask, does C map to S1 or does it not even map to S2? As you can see, whenever something maps to S1, it will also map to S2 because S1 maps to S2 homomorphically. But not there could be a gap. In theory, there could be a gap. There could be things that do not map to S1, but do map to S2. But the promise in this context now is that all structures that we consider, all input structures for this decision algorithm, actually fall into one of these two categories. Or we could also say, whenever there is a middle case, whenever we have a structure that lies in between, we can give whatever answer we want. Yeah, this is the promise part somehow, that we only consider these two cases. I said that PCSPs are a generalization of CSPs, and this is easily seen just if we look at the PCSP of S1 and S1. This is just the same as CSP of S1. Again, there are many computational problems that can be seen as PCSPs. For example, approximate graph coloring problems. For example, I listed this here, the PCSP of K3 and K5. We could ask, given a finite graph, we could ask, is this graph 3 colorable or is it not even 5 colorable? So does it not even map to K5 homomorphically? Yes. An important technique to solve PCSPs is the so-called sandwiching method. And to use this method, we need sandwiches. And what is that? Well, for a template of a PCSP, so for such two structures S1 and S2, as described above, we say that another structure in the same signature, is a sandwich if it lies in between the two homomorphically. So if S1 maps to A homomorphically and A maps to S2 homomorphically. And if we have such a sandwich, this means that to solve the PCSP, we can also just solve the CSP of A. Because whenever we have a structure, whenever such a C maps to A, it will also map to S2. And therefore, by the promise, we say yes, because it then also has to map to S1. And whenever something does not map to A, it can also not map to S1 homomorphically, and therefore it can also not map by the promise into S2. Yeah, this is why we can, if we have a sandwich, reduce this PCSP to solving a CSP. And up to now, every tractable, so every polynomial times solvable PCSP, to my knowledge, can be reduced actually to the CSP of a tractable sandwich, so of a sandwich with an easy CSP. However, not always are these known sandwiches finite. So it could be that we start with two finite structures, S1 and S2, but we then end up with an easy but infinite sandwich in between. And the question whether these structures, whether this can actually happen, whether this is just because we didn't look thoroughly enough, or whether this can be necessary structurally, has been a big question. It has been answered since. So are there any finite PCSP templates, S1 and S2, such that no sandwich in between that is finite can be tractable, can have a polynomial time solvable CSP? Are there such PCSP such that no finite tractable sandwich exists, but there is a tractable infinite sandwich? So we can stuff something in between that is infinite and has an easy CSP, but there is no such thing that is finite. Yes, it has been answered, as I said, in 2019 by Libor Barto. He found an example. However, his example was, in a sense, not very nice because it did not fit into the scope of the conjecture we are talking about today. So it was not a reduct of a finitely bounded homogeneous structure. In fact, for those of you who know that notion, it's not even omega categorical. Yes, so there is a counterexample, but not a really nice one. And so Libor Barto also asked whether there could be an omega categorical example, whether this could be found. And one could also ask the question whether there could even be examples in the scope of the conjecture, so reduct of finitely bounded homogeneous structures. And the answer to this question is yes, there are. This is just the theorem we proved. Namely, whenever we have a reduct of a finitely bounded homogeneous structure B, we can, from this, construct a new reduct of a finitely bounded homogeneous structure, similar to before. And additionally, a PCSP template, such that the first few things will sound similar to you than before. So nice properties transfer, PP constructing K3 transfers. The CSPs of A and this new A prime are efficiently interreducible. But now also A prime is a sandwich for S1 and S2, and S1 and S2 is not finitely tractable. So in particular, if we start with an A reduct of B, finitely bounded homogeneous, that is tractable, that has a polynomial time solvable CSP, then doing this construction from the proof, we get a sandwich, S1 and S2, that has a tractable infinite sandwich A prime with nice properties, but it does not have a tractable finite sandwich. And this answers the question posed by Libor Barto. So we now know that these exist. We now even know that there exists an abundance of them because there are many tractable reduct of finitely bounded homogeneous structures. But now I want to go back a step and answer the question 1 and 2 in a more lengthy way and show you the construction that ultimately also allowed us to answer this question. Some extra work. And so let's do that. So to do that, I need a few more notions on nice infinite structures, one could say, or on structures, or on properties of infinite structures that we would like to preserve in our constructions or get in our constructions. There are 4 of them. We call, again, A at most countable relational structure in a finite signature. We call A CSP injective. If we have that for all finite tau structures B, so for all instances of the CSP of A, we have that B maps to A homomorphically if and only if it maps to A homomorphically and injectively. So if there is a homomorphism, there is also an injective homomorphism. Popular examples of this would be, again, Q with the order. You can imagine whenever we have a structure with just one symbol, the order symbol, that maps to Q homomorphically, this just means that we can complete the relation on this finite structure to be a partial order. And this then always embeds into Q. Sorry, it doesn't embed, but it always it doesn't embed, but it can always be mapped injectively because we can split up. Yeah, it doesn't embed because it's not total. The second example, I'm not sure whether all of you know it, but the random graph, this is just the universal countable simple graph. So a countably large graph that does embed all finite simple graphs. And for similar reasons, this is also CSP injective. Whenever a structure with one binary symbol has a homomorphism to this, we can somehow complete the relation on this finite structure to be a graph, and this then embeds into the random graph just by the properties of it. The second notion I want to talk about is omega categoricity. We call a structure omega categorical if, as I said, always countable. We call it omega categorical if for all n, we have that the action of the automorphism group of A on n tuples, for any n, only has finitely many orbits. Some of you might know this notion as the automorphism group is oligomorphic, but in our context, this is equivalent, and this is the nicest characterization for our purposes, which is why we are going to use that. Again, we have the same examples. Q with the order is even homogeneous, and therefore, it's an easy exercise. Omega categorical in this sense. And the same holds for the random graph. This is also homogeneous. Yes, the third notion, instead of a model complete core, we call a countable, at most countable relational structure a model complete core if all of its endomorphisms are even embeddings. So first of all endomorphisms are injective, and they do not only preserve all relations, as in general all homomorphisms do, but they also have to preserve the complements of all relations. Yes, in Q, this is the case because order preserving functions have to be injective, and the order relation is total, so preserving the complement is not that hard, and so all endomorphisms here are already embeddings. The random graph is not a model complete core, however, because you can imagine that, for example, an endomorphism could map to points A and B to other points where a new edge is introduced. The original vertices did not have an edge, but we mapped into something with an edge, and therefore the random graph is not a model complete core. However, there is a subgraph of the random graph that is a model complete core, and that is K omega, so just the complete graph with countably many vertices. And the fourth and last notion, but maybe the most important one for today, I already used it, is that of no algebraicity. We say that a structure has no algebraicity if for all n and for all n tuples A bar, the stabilizer of A bar does not stabilize anything else. So it does not stabilize any A prime that is not already in A bar. One could also rephrase this and say that any first order property relative to A bar that we can define cannot be enjoyed by just finitely many points or just one point. But if there is one, there have to be infinitely many points with the same property with respective to A bar, or there is none, obviously. Yeah, this is also a strong assumption in many classification results in the realm of CSPs. For those of you who know MMSNP, for example, in the proof of the complexity dichotomy for that, no algebraicity is assumed. In homogeneous structures, which we are often dealing with here, no algebraicity is equivalent to the strong amalgamation property of its age. So a strong property that is good to have, one could say. Yes. So now we have the structural notions that we need. to talk in detail, but we also need a few notions concerning efficient computation, and that is data log. I already mentioned before in the short answers that I claimed that there were efficient interreductions between CSPs, so reducing one to the other and back between A star and A. And this is where data log comes into play. The definition, data log extends existential positive first order logic with formation rules whose semantics is giving or is specified using inflationary fixed points. That maybe sounds a bit much, but it's for our purposes, I think it's enough to just look at an example, look at how such formation rules look and what an inflationary fixed point is in this context. And this will already show us to which extent we need data log, basically. So let's look at this example here. Imagine that we have a structure, a relational structure, whose signature contains this order symbol. It does contain the regular order symbol. It does not contain the boxy order symbol. And now we apply this data log program. We apply these formation rules iteratively until at some point nothing happens. So in our structure, as I said, the order symbol is in the signature, and for all pairs in the first step, for all pairs that are in this order relation, we derive that they are also in the boxy order relation. In the first evaluation, the second line will not do anything because at the beginning the boxy order is new and empty, so this doesn't do anything. But then we apply this formation rules iteratively, and in the next step we will have some x and z that are in relation, hopefully, and we will also have some z and y in relation. And now this formation rule will also be applied, or will be applied and actually do something, and we will derive again boxy order symbol of x and y. And then we will just iteratively apply this over and over again until at some point this inflationary operator, because the operation only gets bigger in every iteration, will reach a fixed point. In particular, for example, if we start with a finite structure, at some point, so smaller boxy order starts empty and then gets bigger and bigger. At some point, it will stagnate, and the relation that remains then, the formula defining this relation is then called the inflationary fixed point of this boxy order. I think it's not hard to see in this example what the inflationary fixed point will be, because at first we inject the order into x and y, and then we just do transitivity over and over again. And so the inflationary fixed point of this data log program will just be the transitive closure of the input relation. So that is how this works. We say that a CSP of some structure A is solved by data log if there is a data log sentence. So if there is a sentence built from a data log formula like this, that identifies all no instances of the CSP. So it identifies all structures that do not map homomorphically to A. For example, if you look at the example above that just calculates the transitive closure, this solves the CSP of Q with the order, because something does not map homomorphically to Q with the order if and only if it's the transitive closure of the corresponding relation has a loop, because then it cannot map. And it's an if and only if, actually. And so the sentence, there is an X such that X and X is in the transitive closure of smaller. This is what it actually says here. This solves the CSP. Yes. It's maybe worth noting or interesting to those of you who know the notion that data log corresponds to bounded width often. For example, for finite domain constraint satisfaction problems being solvable by data log is just the same as having bounded width. And also the evaluation of data log formulas runs in polynomial time, which will be, which is efficient. And so if something has bounded width, if something is solvable by data log, it will be tractable. But this last thing will also be important concerning the reductions I promised at the beginning, because in the short answers, we did not talk actually about solving CSPs via data log, but we talked about reducing CSPs to one another. And this is actually the more important thing for us today. So for two different structures of possibly different signatures, we say that the CSP of the first one, data log reduces to the CSP of the second one if we have a mapping from instances of the first CSP, so finite sigma structures, to finite tau structures, such that yes instances of the first CSP are mapped to yes instances to the CSP of the second, and no instances are mapped to no instances. So a reduction, and such that this mapping I of C or I can be defined using data log formulas. So in this case, we say if we can, via these data log derivations, reduce the CSP of A to that of B, we say that the CSP is data log reduce. And in particular, whenever B is in a complexity class like P, so polynomial time solvable, that already contains data log, and then we reduce something using data log to the CSP of B, also this other thing, so CSP of A in the context of here above, will also be in P. So data log reductions, they preserve or they transport tractability from B to A somehow. One last thing, because I talked about PP constructions at the beginning, data log reductions are they are not contained, they are not subsumed by PP constructions. In fact, it's the other way around. PP constructions can always are subsumed by a special kind of data log reduction, but not the other way around. And also in the construction I'm going to show you next, what we are doing there cannot be done via PP constructions, but actually needs data log reductions that are not PP constructions. Good. Enough about algorithms and programming. Let's get into the construction. So there it is. Okay, so we want to give the long answer to question 1, whether we can impose any additional structural assumptions on structures in the scope. So as I already said in the short answer, we want to have no algebraicity, or to eliminate algebraicity if it exists. And we also will get CSP injectivity. So if there is a homomorphism from a finite structure, there is also an injective one. And we want to do that while preserving nice properties. And the way in which we do that is by blowing up or by inflating our structures in a nice way, in a clever way, which I'm going to show you now. The construction is called the wreath product. Some of you might know this from group theory, and it's no surprise that we call it the same. But yeah, I will tell you why in a minute. So how does the wreath product of two structures look? Given two structures, B and C, B is of signature sigma, and C is of a disjoint signature rho. Their wreath product is the structure we get by replacing just every point of B with a copy of C. You see the resulting structure on the right. And also having the new relations, namely the row relations, so those from C, are now only living inside of each C bubble, so inside of each copy of C. Then we have the sigma relations of B. Those were between the points of B, and they are just copied to the entire bubble. So every point in this bubble here is in the blue relation to every point in this bubble. I hope you see the laser pointer. And we also have one new relation. It's called E. It's an equivalence relation, and it's just a relation 2 points are in the same bubble. So this is a class of E. This is a class of E. And so one could also say that this new relation E is a relational congruence with respect to these blue and these green relations. So with respect to the sigma relations. This is how we construct the Reith product of these two structures. The reason why we call it this way is that the automorphism group of the resulting structure is actually isomorphic to or equal to the automorphism to the Reith product of the original automorphism groups. And this has the effect that many nice properties of structures that can be phrased as properties of their automorphism groups will then transfer. For example, I talked about omega categoricity, and I said this is if the group only has finitely many orbits, that the action of the groups. And I talked about no algebraicity and said this is if the group doesn't stabilize anything else. These things, because the groups are constructed, the automorphism groups are now constructed in this nice way, they transfer. If the right structures have good properties, then also the Reith product will have them. And we didn't do the Reith product for just any structure, but specific ones. And how did the construction exactly work? So we started with tau with a reduct of a finitely bounded homogeneous structure, namely the reduct with the signature tau. And what we then did was we constructed this new B tilde I already mentioned by just taking the Reith product of B with Q with the order, and also adding afterwards a global inequality. So just the global inequality relation on this resulting structure. And because Q with the order has no algebraicity, this transfers to the new automorphism group, and also now this B tilde also has no algebraicity, and therefore also all its reducts do not. And now we have A star, which is just defined as the reduct of B tilde using the relations from A, and also this new equivalence relation we got and the inequality. The no algebraicity from B tilde transfers to A star. And further, A star is now CSP injective. And we have that A star PP constructs K3 if and only if A does. And the CSPs of the two, A star and A, are actually even data log interreducible. This is the efficient interreduction I talked about before. Just to maybe sum this up, or have it in a compact way so that you can also compare it to the next result, which will be faster. So just any A non-trivial reduct of B. Non-trivial, it's not that important here. This just means that there is no constant endomorphism. Then we get this A star that is CSP injective, interreducible CSPs, constructs K3 if and only if A does. And here you see the nice properties that transfer, which are also often of use. So model complete core transfers and Ramsey transfers. Now I will, before ending, now go to the more or less detailed answer of the second question, namely whether we can impose significant algebraic assumptions on the polymorphisms. One more notion for that, we call a structure polyinjective. If all polymorphisms are essentially injective, I already teased it at the beginning. As a matter of fact, a structure is polyinjective if and only if the polymorphisms all preserve this relation. So, the relation that's stated here. To see whether, or to enforce this, one can try and add this relation I4. And actually, whenever we start with a CSP injective structure, which we got in the previous construction, if we add then I4, we get data log interreducible CSPs, but we lose CSP injectivity. And if we started with no algebraicity, we still had that, And now in total, I again show you the entire statement. And yeah, in purple, you see what changed. So yeah, A and B are the same, but now we get A star with the added I4 and B tilde with the added I4. Now we have that A star I4 is polyinjective, so only essentially injective polymorphisms. Yeah, and the rest is the same, just always the I4. It doesn't temper with our nice properties. So what that tells us is that all identities that characterize tractability in the conjecture must be essentially injective. At the beginning, when talking about the conjecture, I had this pseudo-Siggers identity. So alpha tilde S of something is equal to beta tilde S of something. And as you see, this is necessary. S of something is equal to S of something else. This is clearly not injective. And so for an identity to have a chance of characterizing tractability of these infinite domain constraint satisfaction problems, that it needs to be injective, or it needs to be able to be injective. And with these endomorphisms alpha and beta, it ensures that. And so this gives a hint of why pseudo identities are necessary, or it tells us why, and also how they could, which identities have a hope of maybe one day actually doing the characterization. Yes, and this already sums up my talk. Thank you so much for watching and listening. Yeah, that's it. Thank you.